As I was saying, we'll try and obviously get back to you ASAP with a plan. So we have the benefit of the test was we can see where maybe we need to allocate the hours. So it'll probably be in reverse order. The physics maybe should get the most hours, and then the chemistry, and so on. So we have a good picture now that you've done the test. Now I know that the funny thing is with the physics is
physics is easy.
It's not too bad. It's not too bad. It's just you haven't seen the stuff and you haven't practiced, you know. Anyways, as I was saying, I know we're down for a tutorial, but I think I would like to make this the class, because then we have the semester finished, and then our next class, which is Wednesday, I think. I'm not sure about that. It's Wednesday, I think.
Wednesday. Oh no, tomorrow morning, yeah. One lesson. Two lessons soon.
A double, okay.
Yeah.
9 to 11. My favorite class.
Oh, you only have one math class this week?
It's reduced for this week because of the EAP stuff or something going on, and then it's back to normal after that.
Is this thing the one that we have to...
That's the computer one, yeah. We'll talk about that later in the week. Anyways, I thought we'll finish the semester today, because then everything after this will just be a tutorial, because we have everything covered.
So this is
Okay?
the last lesson.
For the semester, yeah.
This is for the second semester?
No, this is the last lesson of semester 1.
No,
Oh yeah, that's for the second semester. Yeah, correct. Yeah. Okay. So what we're going to have a look at now is something called probability trees. Guys. We're having a look at something called probability trees. These are pretty straightforward, and they're pretty common in the exam, and usually the marks are quite generous for them, and they're not very difficult. So we use a probability tree when we have a series of AND events. So what I mean is it works well when you have a situation like A happens and then B could happen and then C could happen. You know, when we have a sort of chain like this. A simple example to show you how probability trees work. We could start with talking about looking at tomorrow, the weather, and getting to school on time. So for example, you could have a situation where it either rains tomorrow or it doesn't rain tomorrow. Not rain, okay? And maybe the weather forecast is a 0.8 for rain, so therefore 0.2 for not raining. Obviously, fair enough. And you can understand that whether you're late or not is influenced by whether it rained or not.
We're going
So,
to be late anyway, so.
Okay, very late then. So, if it rained, do you think that would make it more likely for you to be late or less likely? More likely. So, you can have late, not late, and then following from not rain, you can have late and not late. Okay? So maybe this will be 0.7 and 0.3, and maybe this will be 0.2 and 0.8, something like this. I kind of have them switched around. So if it's raining, then there's a 70% chance of you being late. It didn't rain, then there's a 20% chance. Yeah. So you can see that this tree represents sort of two worlds. A scenario where it rained and a scenario where it didn't rain. Okay. What we'll have a look at now is how we use this tree for calculations. So I'll just let you copy that tree, and then we'll have a look at some examples. I'll put them up here. You got that? Did you write that down? Yeah. Some of you have seen probability trees before, perhaps? Yeah. I suppose you might see a little bit kind of in genetics. I'm not really sure you have the branches of the possibilities, right? Yeah, and maybe there's tables as well. Yeah. Okay, so let's take something really easy where there's not really any calculation. I said the probability that it rains. Well, that's straightforward. What's that?
0.8.
Yeah, 0.8, isn't it? Now, what about if I said something like the probability tomorrow it will rain and you'll be late? Now, how do we work this? This is an and. What is it, yeah?
0.73.
No.
Why? 0.7 times 0.8.
Yeah, 0.8 times 0.7. What you're doing is you're saying rain and late. And the rule here in probability is an and means a multiply. Who was I talking to about this before in class? Not in this group, in the other group. Anyways, and is multiply and or is plus. Okay. Abdul, was it? Oh. That doesn't matter. Anyways, what is that? 0.8 times 0.73. What's that? 0.6? 5.6. Okay. Now let's do something a little bit more challenging, more typical of the exam. Probability of just being late. Now, there's actually two ways to be late. That is rain and late, or no rain and late. So in other words, it's like you add up all the branches. You can be late this way, rain and late, or not rain and late. You've got two paths. So path 1 is 0.8 times 0.7, or path 2, what's path 2? 0.2 times 0.2. So that would be 0.56 plus 0.04, which is 0.6. So you have a 60% chance of being late. Okay? Now, probability of not being late. What's that? Which is?
1 minus 0.4.
Yeah, 0.4. If you had a 60% chance of being late, then you have a 40% chance of not being late. Yeah. Okay. You have that? Yeah. Now, in a moment, we'll have to talk about. Do you remember the vertical line? What does that mean? Conditional, given that. Yeah? So we need to think about how to calculate that here. Yeah? Can I go to the sides? Nikita? Yeah. Okay, so look. Remember, we were doing our tables. You could have, for example, A and not A. B and not B, for example. And then here you have your totals, right? And then here is the total of everything, okay? I just want to put some not numbers. I just want to put some letters in just to make it easy for us to reference. So I'll just call it A, B, C, D, just to give it letters. And I'll call this one N1, N2. And then here N3, N4. And here, let's just call it capital N. I mean, I'm just giving it letters instead of numbers. Okay, you can pretend there's numbers there. So, suppose I ask you for something like the probability of A given B. Now, how did we do that when we had tables? Probability A given B. Well, we were just looking among which group? The A's or the B's? No, the probability of A given B means we're just looking among which group?
A group.
No.
B.
Yes.
Yeah. Just whatever you think the answer is, just go with the opposite, okay? Right, so we're just looking among the B. It's given B, among the B. Remember, it's like probability of a tea drinker among the females. Do you remember? We did that example. So what's the denominator here?
B.
Yeah. N1
Yeah.
among the B's. Okay. And what is the numerator?
A. Small A. Small A.
Which small a, yeah.
What? Why? Isn't it? Never mind.
Isn't it small a?
Yeah.
Isn't it the
Yeah.
whole
Is
A?
it?
Because
No.
it's a capital A.
No, it's the name.
We need numbers.
I can see that.
I think
see that.
numbers is better. I think numbers is better.
Really?
Yeah, yeah. I think numbers is better.
Okay.
It's quite confusing, right?
Okay.
Yeah.
Hang in there.
Yeah.
Hang in there. Hang in there. Now, watch this, please. What I'll do as a little algebra trick, I'll just divide the top by n and the bottom by n. And the reason I'm doing that is I'm giving us an interpretation of what the top is. This A divided by the total n. What does that represent as a probability? In other words, what probability do I put here so the answer is A over n? A and B. Good. And here, what would this represent? What probability? So that I end up putting this number over this number.
B.
B. Very good. Very good. This is the formula for conditional probability. It says the probability of A given B can be calculated by looking at the probability of A and B over B. Okay, this is the conditional probability formula. So I'll just put it in a box here. A given B is the probability of A and B over B. Okay, you should make note of that. This is what we'll need to use back in the main example. So can you write this down? You don't need the proof. The result is what we need. I was just trying to show you where it comes from. Okay. No. Are you writing the proof down?
Yeah.
Oh, okay. Well, it's good to know where it comes from. Yeah? Yes? Yeah. Okay, so look, let's go back to this one here. So suppose I ask a question like, number 5 here. What is the probability it rained given that the student is late? So you know the student is late. What is the probability that it rained? Okay, so according to our formula,
Probability of R
and L over
R.
no L, the second one. Now this is good because we know both of these, don't we? Rain and late is 0.56 and late is, we said, 0.6. So what do we get here? Being quite high, being nearly.
Why late 0.6?
We calculated that early. Earlier.
0.93.
No, that's right there.
Ah, yes.
What is it?
0.9333.
Okay, so 93% then. Yeah? Okay. Right. Now, I think we'll do, yes, I'll give you one to try, and then we'll look at an interesting medical one then. So can you add that last one there? Rain, given that student was late. Yeah, I suppose the other formula is the not one, where not A is 1 minus A. Okay. Have you got that? Yeah? Yeah? Scroll down? Yeah. So you have three boxes, we'll say, and I'll call the boxes A, B, and C, but you don't really know which box is which because it doesn't say it on the box. I'm only giving them the names A, B, and C so I can reference them, okay? But the boxes are identical. You don't know which is which, okay? And the first box will say there are 3 red and 1 green. In the second box will say there are 2 red and 2 green, and in the last box will say there's 1 red and 3 green. Okay. So the way this game works is first you pick a box, pick one of the 3, and then you just take a ball out. Okay. So this game can be represented nicely as a probability tree. How many branches do we have first? 3. We have A, B, C, and then off of each one we have 2. Off of each one, because you can get red or green, red or green, red or green. Okay. So with the help of a probability tree, I have a couple of questions here. So the first one is, what's the probability of getting a red ball? And then you can answer the next one quite easily. What's the probability of getting a green ball? And remember, green is the same meaning as not red, because there's only 2 choices here. It's yeah, you see the thing now. And then we'll make it part 3, so there's 3 parts here. What is the probability?
Red and
No, you're only taking 1 ball out, so you just pick a box and then pick 1 ball out, yeah. No, you're only taking 1 ball out. I don't want to take 2 out.
yeah, red. Then green. Like I'm taking 1 ball out.
Are you replacing it? That would please go over to
How can you be taking 1 out when you take 2 out?
I'm taking red.
Yeah.
Then put it back. And take
Watch. This is 1. This is 2.
yeah.
That is different to 1. Yeah. Right.
Oh my god.
Indeed. Okay. Right, you're breaking my train of thought. The last one is the probability that you actually picked box A, given that you got a red ball. Okay? So, not really. Okay. Give that a try. See if you can get this. I'll give you the answer in a minute. Yeah, you should draw the diagram.
Do we have to?
No, you don't have to unless the question asked you to in the exam, which they usually do.
What's the first number or R?
3 red, 1 green. 2 red, 2 green. 1 red, 3 green.
3.
Oh, the mute symbol is putting it out, isn't it? Okay, let's have a look at some calculations here. So what are ABC? What are the probabilities here? Well, 1 over 3 for each, isn't it? And then red, green, red, green, red, green. 3/4, 1/4. Half, half. 1/4, 3/4. So probability of red should be 1/3 times 3/4, yeah? Plus 1/3 times a half. Plus 1/3 times a quarter. So that's 12. Yeah. Oh, actually, that's, yeah, a quarter plus a sixth plus a 12th, is it? And you said that adds up to a half? Nice, okay. And so what's the probability of getting green? Yeah, because it's the opposite. So 1 over 3 was the first branch. You have 1 in 3 chance of getting either A, B, or C. Yeah, and green, so would be a half as well, wouldn't it? Because it's the opposite of getting a red. So the last one, I don't know if you got it yet. The probability of A, given that you got a red. So A and red over red. Yeah. Well, I know that red is a half, and A and red is 1 over 3 times 3 over 4. So that's a quarter over a half, which is a half as well, coincidentally. Yeah? Is that still visible? Yes?
Yeah.
Okay.
Why do you put the numbers like 1 over 3 for each ABC?
Ah, because I'm assuming they're equally likely. You know, if I gave you 3 boxes, and one of them's A, one of them's B, one of them's C, you know, it should be 1 over 3, right? There's no reason to think that one box will be more likely.
Is it okay if like do the branching?
Yeah.
I put like red is 3 and green is 1.
That's, oh, no. No, in the exam they want them as fractions. So, yeah, that's not okay then. Got that?
Well, I didn't use the diagram. I just did like the total of red, the total number of balls. Can that work? Total
No.
number of balls, total number of red.
Oh! Oh, I understand. Yes, for this precise question, it's not always going to work. That only worked because each box was equally likely to be selected. So if I made some small change where I said something like, oh, box A was slightly bigger than the other 2 boxes, and so people more likely pick that one, so it's not an equal chance, you know, then that wouldn't work. Yeah. So yeah, answer your question, it only works because of this, which is actually not so common in the exam. Okay, I want to do a bio example next. Yeah.
It equals to what? Half?
Finally a half, yeah.
Did you add the greens as well?
For which part?
For the red?
But which part? For the last part?
No, the first.
Oh, greens are there. 1 over 4, 1 over 2,
No,
2
I
over
mean
4.
in the equation, the probability of red. It's 1 over 3.
Oh, I didn't look at the greens, yeah. It's 1 over 3, 3 over 4. 1 over 3, 1 over 2. 1 over 3, 1 over 4.
Okay.
Yeah? Yeah? Guys, you got that? Has that? Yeah, I can scroll down? Okay. Some vocabulary bio-specific or sensitive and specific. Now, guys, what's wrong? Are you looking up? Yeah. Right. you have talked about testing in biology and chemistry, right? Like, I mean, you've talked about maybe testing if something is an acid or a base, or testing the presence of an enzyme or a protein or whatever, right? And of course you understand that these tests are never going to be 100% perfect and accurate, right? So I wonder if you've come across these words in the context of testing the presence or absence of something. So in biology it could be a pregnancy test or protein presence or something like this. Anybody know the meaning of these words in this context? No? Yeah, accuracy is fine, but we can be more precise, okay? No, not this. It has a precise meaning. So when we talk about how sensitive a test is, we talk about the probability of getting a positive test result given that, let's call it a disease, for example, given that the disease is present. Okay? So the sensitivity of the test is how likely the test will give a positive result for the disease given that the person actually has the disease. Okay? This number is not 100%. You would like it to be 100%. You would like it to always say positive test result given that the disease is present. Okay? But it's not in real life. So, specific. That is kind of like the opposite. Is what is the probability that the test result is negative given that the person does not have the disease? Now, you tell me, let's look at an example. What would be good numbers here? You know, what type of numbers would fill you with confidence? If somebody said this test is blank percent sensitive, 99. And what would we say? 99 as well for the other one? Yeah? For example? Okay. So we could say that the test is 99 sensitive, 99% specific. And let's also write down how likely it is for a random person in the population to have the disease. So let's say that it's not a particularly common disease. Let's say there's a 0.01 chance here of having the disease. Okay, let's just look at what the tree looks like. First of all, the person can start off by either having the disease or not having the disease. Then they go get themselves tested. And the test result comes back positive, or it could come back negative. Here it could come back positive, or here it could come back negative. If they have the disease, what's the chance the test will say they have the disease? 99. And the test saying, oh no, 0.01. No, you need to ask me questions. You can't ask me to repeat myself. Yes?
Why do you point?
Thank you, that's better. So, if it's a 99% chance that it says they have the disease, then it's 1% chance that they don't. Okay, now let's say they don't have the disease. What's the probability that the test will say they don't have the disease? 0.99. And that they do have the disease? 0.01. To begin with, how likely is it that they actually have the disease? And then 9. Now, can we look at the mistakes? Here, this is a good result for the test because the person who has the disease was diagnosed as having the disease. This one here is also good for the test. The person who does not have the disease is diagnosed as not having the disease, so this is good. But these two represent the test failing. In this case here, we call this, you could probably understand why, a false negative. That is, they were told that they don't have the disease, but they do. And what do you imagine this one's called? A false positive. That is, they were told that they have the disease when they don't. Of the 4 outcomes, which is the worst outcome for the patient? False negative. Why is a false positive not so bad? Yeah, they'll have follow-up treatment where it will become clear that they don't have the disease. You know, maybe they'll have further testing, X-rays or something like this. Okay. So, before I gave you this question, you wouldn't have been able to answer this rather simple question that I'm going to pose. What is the probability that you actually have the disease, given that you were told the test was positive? Now, you might seem like it's 99%, isn't it? But no, can you see how that's not the same thing?
Yeah.
Probability of having the disease, given that the test is positive. Well, you'll have to calculate it. So by using the formula, calculate this, please. Now you understand that this is really the number you want to know. The doctor says to you, you have a positive test result. You want to know how likely it is you have the disease. So you can calculate it now. 1.01. You have a 101% chance of getting the Not only do you definitely have the disease, you have a 1% chance of having another disease as well. No, not this. 0.01. You have a positive test result and there's only a 1% chance you have the disease. No, it could be. It's certainly more believable than a 101% chance.
0.01.
That's what you got as well. Yeah. What's your calculation? What's on the top? Probability of the disease and positive over probability of positive. So, on the top, disease and positive is 0.01 times 0.99.
Yes.
And on the bottom, positive is 0.01 times 0.99 plus 0.99 times 0.01. This is 0.5.
Why did we time plus?
Hang on, she was before you. Go ahead.
Why does the top part, you don't have to type 0.1 times 0.1? It's only that one.
Huh? The top one is disease and positive result.
Why is it just disease and positive result? It's not disease, positive, and negative.
No, but this is the formula. This is our formula for P, A given B. Remember?
Yes.
We did it 12 minutes ago. A and B over B. Yeah.
Oh, okay.
Oh, nobody said I have to remember things in class. Oh. Okay. Now, I hope this result seems a little bit surprising. 50%. So, I want you to put yourself in the waiting room. Okay, you've just done this test for a deadly disease, and the doctor comes out and says, well, the test comes back positive. And you say, how accurate is this test? Well, if you have the disease, it's a 99% chance it says you have the disease. And if you don't have the disease, it's a 99% chance that you don't have it. And it's a positive result. And so you're thinking, man, I've got the disease. But really, you only got a 50-50 chance of having the disease. Now, what precisely is the number in this calculation that is making it seem so strange? Because both these numbers seem good. They seem believable. Yeah. Strangely, how probable the disease is has a bearing on how accurate the test will be. So if I was to make even a small change, let's say the disease is 2% prevalent, then let me just change that in red. If this was 2% prevalent, what numbers change here? This is a 2, this is a 2 here, but this is still a 1 because that 1 is because of that. What number do we get now if we backspace and change those to 2's? No, this is still, oh sorry, you're right, this one is 9.8, thank you. you see, that's starting to jump up quite significantly, isn't it?
Why did you
0.67. Oh, I just want to give another example. So let's do one more. Let's say the disease is 5% prevalent. Okay, so let's make it a 5% prevalence. 5%, so that would be 5%, wouldn't it? That would be 5%, and that would be 95.
That would be like 80% something.
Maybe even more. Let's see where we get. Because going from 1 to 2 made it go from 50 to 67. Okay, so what is it at the 5%?
0.84.
Okay, so yeah, about in the 80s then. 80, so there's an 84% chance you have the disease. Now, even that doesn't sound too bad. That means you've got a 1 in 6 chance of not having the disease, even though the test is positive. Which is, you know, if it was a life-threatening disease, you'd be happy with that. Much happier than 99%. Okay? So again, do you understand the reason I'm doing this example, like the example last time with the kidney stones, is to show you, even with quite simple and seemingly quite clear numbers, your result is not guaranteed to be the obvious intuition. Because, I mean, this test looks fantastic until you actually do an example calculation here. Okay, this is an important state. There's an important case study example in medicine when the HIV disease first appeared in the 1980s. There wasn't really great tests for diagnosing them because it was still a new disease. So I think these numbers could have been something silly like 0.8 and 0.85 and 80, something like this. Okay. And in the early days of HIV, this number here would have been less than 1% of the population, right? It would have been something like maybe, oh, I don't even know, less than 1%, okay? So with my example of 0.99, 0.99 and 1%, what was the likelihood you have the disease? 50-50. So you can imagine 0.85, 0.80 and let's say 0.01, it was less than 50% chance. That means the doctor says the test result is positive and you have a better than 50-50% chance of not having the disease. Okay, so again, I'm just trying to highlight, this isn't baby simple probabilities. You know, it's you can get some very interesting examples with this. Yeah, I don't know if you talk about this stuff at all in biology. Do you do any discussion of testing or anything like that?
When you explain false positive and negative.
Oh, he covered false positive and false negative. Yeah, okay, in passing then. Yeah, which test was it?
It's for an experiment.
Wait, it wasn't for baking a cake? Of course for an experiment, but what experiment?
No, just say in general.
Yeah,
Just said in general before we started.
Oh yeah, but what was the context? He didn't just walk in one day and say, hey,
Just explain how graphs work.
Yeah, you just
the
explain like
enzyme.
what's the point of independent variable and
No,
when you say
it's enzymes.
prevent or something.
okay.
It's variables.
I just remember the class.
Yeah.
Enzyme activity. And that was the first time we looked at a graph.
So,
That was the very first class we looked
yeah,
at a graph.
it seems like you forget your biology as easily as forget your maths, perhaps? No. No.
Okay.
Oh, indeed. Yeah. Okay, so look, for Tuesday, or next class, you really want to get all of these for exam purposes, 1 to 7 is good for the exam. Now, the 8 to 12 are a little bit harder, but if you can do 1 to 7, then you should be good for the exam. Probability tree is a fairly standard section A question in the exam. It's pretty straightforward. Okay, now we have a double class in the morning tomorrow. Yeah, so we'll start looking at exam papers.
So tomorrow we bring our laptops.
If you like to, yeah, because we'll be opening up papers on Moodle. Yeah. What's that? When I changed it to 0.05, it became 84%. Oh yeah, sorry. It was like 0.84.
Yeah.
Yeah. All right, we'll wrap it up there. Try to get half of them done at least.